Hello, learners. Welcome to the course on computer architecture design using VHDL. I am Dr. Prerequisites Mukherjee, an assistant professor in electronics and communication engineering. I am the course coordinator for this course. So let us have a quick introduction on what this course is all about. To undergo this course, you must have knowledge of digital electronic circuits. What is Boolean algebra? What are the basic logic gates? What is truth table? How to use K-map to minimize logical expressions? What are the basic combinational circuits, how to design them using basic logic gates like multiplexer, demultiplexers, encoders, decoders, adders, subtractors, etc. What is a sequential circuit, how it is different from combinational circuits, what are the basic blocks of sequential circuits like different types of latches and flip-flops, and how to interconnect them in order to form circuits like registers, counters, etc. So up to this much knowledge you must have in order to go through this course. Now, if you have a course on digital electronic circuits already, then you must have the corresponding lab. And in that lab, you have used breadboards and basic logic gate ICs in order to design some digital electronic circuits, different digital electronic circuits. Combination of it can be combinational circuit or sequential circuit. So you have seen this ICs that you have used, and most of them are 74LS series ICs, which are TTL logic ICs, transistor logic ICs, and most of them are having less than 12 number of gates. Many of them are having only 4 and 6 number of gates on it, logic gates on it. So as a result, to design a fairly complex digital circuits using those ICs, the circuit becomes this much clumsy. The wiring becomes this much clumsy, so that if error occurs, it would be very hard job to identify the error and then modify the circuit in order to make it functionally correct. So circuit designing becomes very difficult if you have only idea of those TTL ICs, transistor logic ICs. So on the other hand, this you already have this information, this type of circuit you have already designed. And in the right hand side, we are having 10,000s of gates, logic gates on a single chip. It's a Atmel's 89C51 microcontroller IC. It has a 8-bit CPU. Along with that, 128 byte RAM, 2 kilobyte of uh, flash memory, and also other peripheral digital electronic circuits like programmable timers and counters, programmable interrupts, programmable input outputs, so many things. So now, how to design this kind of circuit? So when you are having so large number of logic gates, so first of all, you cannot draw even that circuit on a piece of paper. So what is the way to design this kind of circuit? Uh, you must have some knowledge, or so you must incorporate computer aided circuit design techniques in order to solve this issue. So the first step of automatically design this kind of ICs is to describe the digital circuit using some hardware description language. So how to do that? This will be motto of this course. Now this slide describes why to learn this course at all. So through this course, you will get to know how to design and test digital systems using hardware description language. And describing any digital circuit using hardware description language is called RTL level design, register transfer level design. You will know RTL design using HDL. Now, once you are having RTL of your digital circuit, you can go for two different types of synthesis, FPGA-based synthesis or ASIC-based synthesis. FPGA is field programmable gate array, and ASIC is application-specific integrated circuit. In FPGA, we are having sea of configurable logic blocks and interconnects, where you can quickly dump your circuit. You reconfigure them and you dump your own circuit, and you can test it also. Whereas In ASIC, you will be designing a separate integrated circuit for your RTL. So obviously, what are the processes involved in these two types of synthesis are completely different. That we'll be discussing in this course. And what are the advantages and disadvantages we will also discuss. Nowadays, not only designing a RTL of the corresponding digital circuit is sufficient. You must know also how to optimize your circuit in terms of speed and power consumption of your circuit. So, what are the techniques we will discuss in this course? Once you have knowledge, this much knowledge of RTL design, you will be a potential candidate to be to work in the big integrated circuit industries like Intel, IBM, Texas Instruments, Xilinx, Broadcom, etc., etc. Many Qualcomm analog devices, many, many, and you know. These are very big companies. These are the future. They are creating the future. So you'll be part of that if you know this. Also, if you want to pursue your research career in the domains like high performance computing, Internet of Things, artificial intelligence, or biochips, this is the course for you. This slide describes the contents of upcoming video lectures in this course. First, we will have a video lecture on FPGA versus ASIC design flow, where we will discuss about in detail, what are the steps involved in these two types of circuit synthesis. And we will also compare these two type of design techniques. Then we'll discuss the basics of VHDL on a separate video lecture where we will discuss about entity architecture, some data types present in VHDL, those things. Once we know that, we'll go for installation and demonstration of Xilinx IEC design suite on a separate video. The right-hand side diagram in this slide shows Xilinx Spartan 3 FPGA board. So if you have this kind of board, you can use Xilinx IC Design Switch to dump your digital circuit on this board and test it. Now, Xilinx IC Design Suite is used for FPGA synthesis, for ASIC synthesis from RTL. We are having different types of tools from different companies like Synopsys, Cadence, etc. For Synopsys, from Synopsys, we are having design compiler. We can use that in order to determine the power consumption and the area requirement, those things of your RTL if you are planning to go for ASIC synthesis using certain technology file. Now, uh, next, we'll discuss on a video lecture designing and testing of basic combinational circuits using VHDL. Here, we'll discuss what are data flow style and structural style of architecture design. Next, we'll go for designing and testing of basic sequential circuits like D flip-flop and some basic flip-flops. Where we'll discuss behavioral style of architecture design using VHDL. Next, we'll discuss about designing in-bit ADA structure unit and in-bit universal register and up-down counters using VHDL. Now, we are going for in-bit. In-bit means we are writing our code in a generic way so that if we replace n with 8, it becomes 8-bit system. If we replace n with 16, it becomes 16-bit system in this way. How to write your VHDL code in this way also we'll discuss in those video lectures. Next will be designing n-bit ALU using VHDL, which can perform addition or subtraction or multiplication or addition or subtraction or ANDing or ORing operations depending on some select inputs. Once you design ALU, you'll go for RAM and ROM circuit design using VHDL on a separate video lecture. Then we'll discuss about designing in-bit microcontroller using VHDL. What is a microcontroller? A microcontroller consists of CPU along with memory. In CPU, we are having ALU, register files, and control circuits. So everything we have already designed. So just combine them and interface them. It becomes a microcontroller. So how to design that, we'll discuss in that video lecture. And also, at the end of this course, we will discuss designing of some complex circuits like array multiplier, cache memory. Let us discuss the course outcomes. At the end of this course, you'll be able to design and optimize your own in-bit CPU, which contains in-bit ALU, register files, and control circuits within it. You'll be able to design and optimize your own M cross n bit memory. It could be ROM memory or RAM memory. You'll be able to synthesize your circuits in both FPGA and ASIC-based platforms. We'll discuss what are the tools involved to do so, and then we'll be also able to design advanced computer and memory circuits like on-chip routers, cache memories, etc. Not only that, with the knowledge of this course, you can design your own microcontroller, which you fit into your very own project. Like if you are having a drone-based project or a IoT-based project, here instead of using a microcontroller board like Arduino or Node MCU, you can use your very own microcontroller IC. In place of this IC, you can use your own microcontroller IC, which you have designed and optimized on your own. So if you use that, it will not only decrease the cost of your design, but also increase the performance of your design by many folds. So with this, we have come to the end of this lecture. Thank you all.